Let V be a subspace of Rn with dimension k. We say that u1 up to uk for V is an orthonormal basis if for each I from 1 up to k, ui is a unit vector. That is, the norm is equal to 1. And the dot product of ui and uj is 0 for all distinct ij. That is, if you take any two vectors here, they are orthogonal. For example, if you take the standard basis for R3, then this is an orthonormal basis for R3. And if you take the matrix A equals 1 minus 2 0 0 0 0 1 1, then this here is an orthonormal basis for the null space of A. Clearly, these two vectors are orthogonal, and it's not too hard to check that the norm of each of these vectors is equal to 1. So why do we care about orthonormal bases? For one, if you have an ordered orthonormal basis, then finding a tuple representation with respect to that basis is quite easy. So if u1 up to uk is an ordered orthonormal basis for V, then for any vector V in V, the tuple representation of V with respect to this basis is given by the k tuple such that the ith component is given by the dot product of ui and V. So in the first component, we have u1 dot V, and in the second component, we have u2 dot V, and all the way to uk dot V. So for example, if we look at the vector V equals 2, 1, minus 1, 1, and if we let gamma be the ordered basis u1, comma u2, where this here is u1 and this here is u2, then to obtain the tuple representation of V with respect to gamma, we take u1 dot V as our first component, and you can see that it's going to be 4 over the square root of 5 plus 1 over the square root of 5, and that's the square root of 5. And for the second component, we take u2 dot V, and it's going to be given by minus 1 over the square root of 2 minus 1 over the square root of 2, and so that's just minus 2 over the square root of 2, which is minus the square root of 2. And you can check that V is given by the square root of 5 times u1 minus the square root of 2 times u2. So why is this true? Let's first write V as a linear combination of the basis vectors u1 up to uk. And so we have scalars lambda 1 up to lambda k such that V is given by lambda 1 times u1 plus all the way to lambda k times uk. Now I'm going to pick an arbitrary I from 1 up to k, and I'm going to take the dot product of ui and V. Since V is this here, I can write this as ui dot lambda 1 times u1 plus all the way to lambda k times uk. Now I can rewrite this as lambda 1 times ui dot u1 plus and so on up to lambda k times ui dot uk. And now I can simplify this. Because ui dot uj is 0 for any j that is not I, what is left here is going to be just lambda I ui dot ui, because everything else will be 0. And ui dot ui is going to be 1 because ui is a unit vector. It has norm 1, and ui dot ui is the square of the norm. So I have shown that lambda I is given by ui dot v.